play hockey because the ball is funky, right? It flies through the air, bounces, stuff like that, right? Pucks don't do that. So they actually make these little things that ride on Teflon. I was looking at them at Sherwood Ice Arena, right? Okay. Notice synovial joints? Yeah. That's like your joints. There's like something in there that incredibly reduces friction to some amazingly small amount. Let's zoom out here so these guys can see it. Right? So synovial joints, right? Rubber on other solid surfaces, right? Is a 1. To drag the thing is a 1 like this, right? Notice that wet concrete is more slippery than dry concrete. That's a big surprise, isn't it? There we have it, right? Okay. And then if you have studded tires, it's even less because steel on concrete is less, and you're actually increasing your stopping distance 98% of the time, right? But then of course when you need them, there you have it, right? Okay. Ice on ice. How about warm street shoes on wet ice? What do you suppose that is? That's like fall on your arse. This is the story. We were driving on a road in the Midwest, and it was an ice storm that covered the ground with a ½ inch of ice. We were driving on the center of the road. If you hit the brakes on the car just went. It was like on an ice skating rink, right? The car would just sort of skid. We drove on the center of the road because the road was crowned. And if you drove on the edge, you tended to slide off toward the ditch, right? So we're driving in the center. When we meet another car, we're going like 20 miles an hour tops, right? When you meet another car, both cars would slow down. We'd edge over to the shoulders, pass each other, right? And do this. On one of those, the car that went to the side just kept on going. It just went down a hill into this, right? Into this like farmer's yard. There was a farmer right there in his yard, right? Watching cars go by. This guy goes down into the yard. We're like, okay, we better help. Right? We get out of our car, and the first thing we do is just fall, just bam, because our feet are warm, and the ice is just sort of like covered with a little bit of like water, and then when we touch it with our warm shoes, we melt the ice, and we just fell, right? Then, when we fell, we didn't just stay put, we slid down the crowned road to the ditch. We're sitting there like on the ditch, like going, well, there's my car, right? Sitting there somehow, right? Because its tires are cold, right? So then we try to get to our car. We tried walking to our car, like, bam, right? Down we go. The only way we could get to our car, the farmer just said, go, I've got the guy, don't worry about him, right? We run along the ditch, along the gravel on the side of the road where it's not quite so slippery, and slid out to the car and grabbed it. Got in the car, and somehow the car could stay. It was just crazy. You guys get that all the time. When you get an ice storm, it's always like that. In the Midwest, not so much. Okay, it gets cold enough that the ice isn't quite as slippery usually. Okay, and then here it says values are approximate. Now, the second thing you might notice is there's a couple columns here, aren't there? Why are there 2 columns? Because there's 2 types of friction, comes the answer. And what are the types? Static. This is good. Yes, static and kinetic, because we can read the thing, but what do they mean, right? One is moving and the other is not moving, yes? Pushing back to keep it from moving. This is very good. So watch this. Which one is greater almost always? Starting something to move is almost always harder than keeping it going. Have you ever noticed that? That once you get something sliding, to get it started is like, once it moves easily until it stops, and then it's hard to get going again. Have you noticed that? Okay? This is true with ice blocks on ice, okay, for a somewhat different reason, right? Because the ice blocks, if you let it sit still on the ice, it'll actually make little bonds with the ice, and eventually it'll freeze to the ice, right? So when they moved blocks of ice up into the ice houses, there was no refrigerators before electricity, yes? So they would take big blocks of ice out of the lake, quarry them out of the lake with big saws, right? One person would stand under the ice and go, and the other person would be above the ice. Kidding, okay? And they would cut it into blocks. The ice slides like nothing on the ice if you keep it moving. If you ever stop, well, those things are still out there on the lake until the ice goes out in like April. Okay, they're just nuclear welded to the ice. Okay, so that's the concept, is that if the object ever sits still, even if it's not ice on ice, it makes these little chemical bonds that make it harder. They're weak bonds that makes it harder to keep it moving. Okay, now watch this. So you can see it with this guy. I couldn't get it to work with the fancy electronic one, but watch the needle of this thing, okay? First thing I want to do is I want to drag this, and if I drag it with 500 grams on there, it takes about 2 newtons of force. And if I put more weight on there, this is a huge surprise. It takes, well, now it's taking more than 3 newtons of force, yeah? Okay, so the more weight I put on there, the more force it takes. Now let's look at 500 grams. Just watch. If I carefully ease up on the force, watch the needle. Up, 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 up. Oops, it didn't do it that time, did it? Okay, what we're looking for, and it doesn't do this if there's like crap on the counter. What we're looking for is it to go up and then drop down once it starts to move. Watch. You see it? Yeah, it went up, 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 and then it dropped back down. That maximum thing is the static friction force. Watch again. There, I did it just a little bit. Let's try again. There, it really did it that time, right? So it goes up, 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 drops down. Okay? So the sliding thing, the kinetic is to keep it sliding. Static is just to see whether it slides or not. Okay? That's the two things. These are approximate. What's up with the two columns? How are they related? Blah, blah, blah. Okay? So this is what they are, right? Kinetic friction is the force. And I made this way to remember it, right? Kinetic is to keep it going. And static is to start it moving, huh? All me. Okay. So write that down. You'll need that, I guess. I don't know. So kinetic is what we use almost all the time. Kinetic is the most common thing that we use. Static only answers the question, will it slide? Okay? Okay? So the static friction answers the question, will it start? It's an upper limit. Right? So if my static friction, if my maximum, it's an upper limit, it's a maximum, right? It's the maximum force that those chemical bonds can sustain and not let go. And so if my maximum static force is, say, 30 newtons, but I only exert 10 newtons to make it go, well, the static force is only 10 opposing me, right? So if I got this block like this, and it can go, the static friction could go as high as 30, that doesn't mean it's always 30. If I exert 10 newtons this way, it doesn't move, does it? Why not? Well, 10 is less than 30, right? Okay. So how do you keep it from moving? If I exert 10 that way, the friction exerts 10 this way, right? What if I exert 11 that way? It exerts 11 back. What if I exert 20 that way? 20 that way. What if I exert 29 that way? It exerts 29 back. What if I exert 31 that way? It breaks free and goes, the chemical bonds all go, and it starts to slide because 30 is the maximum. What if I exert exactly 30? We'll never do that, I don't know, right? Yeah, or that's just actually a reaction force, right? Why you move back, right? Okay, so that's static. Kinetic is the force. This thing you use all the time. You use it in F equals ma. Okay, you use it in F equals ma. It is the force that opposes the sliding. Okay, and it is the force. It is when you calculate that, and if it is sliding, it always is this force. Okay, whatever you calculate, if it is sliding, the static friction is always that, and that's roughly accurate. It doesn't really matter how fast I slide this thing. The friction force seems to stay pretty constant, kind of, sort of. Yeah, it does change here because there's stuff all over the surface, but there we have it, right? And I'll do an example of this, and we can see what it really is. Always on opposition to the applied force. And the calculated value is a maximum. So now when you read your problems, right, you have to do this whole thing about, is it sliding, is it not, right? What type of surface is it? Uh-oh. Oh, Anna Pakesh, I am too hot. It's like the first time I've been like wearing